Okay, we'll go ahead and get started. And it's our last week of class, which is, it feels like it went quickly. I don't know about you guys, but for me it feels like it went quick. So anyway, today I thought I'll spend a little bit of time lecturing on kind of the conceptual aspects of hypothesis testing, which we kind of didn't have enough time to go over last week. We'll take some time. I can work through some of these practice questions, although I think your TA will work through these in section, and I will also post up solutions to these, and I also posted up some conceptual practice questions that that we can work through today as well. Okay, so let me. I've written a little bit about the final exam, so I hope you guys all took a look at the chapter 7 and 8 practice questions this past weekend. I do feel that it will be helpful in preparing for the final. And this is what I've written about the final exam, which says I expect us to have about 50 questions or so, and it's going to be all multiple choice. And the exam will cover only through chapter 8. I know in the syllabus I wrote that we're going to get through chapter 9, but with the Labor Day holiday and losing an entire lecture, I'm going to have to stop at chapter 8. Okay? And so you'll have about 5 questions or so covering checking conditions to use the central limit theorem. Okay? And so there were a few examples of that in this practice set of questions, and you will check to just kind of make sure that it's okay to use the central limit theorem. The whole idea behind that is, you know, we use the central limit theorem to say that we can approximate the sampling distribution with the normal distribution. It allows us to, you know, use the normal table and all of that, which is very helpful, but it only works mathematically. It only works under certain conditions, and so so we have to do that. Okay, and then you'll have about 10 questions or so covering conceptual topics, and so sorry, this should say conceptual topics from chapters 7 and 8, and we'll spend some time reviewing that. Kind of have to go over the conceptual ideas. And then you got 25 questions of statistical inference, which is very similar to the questions that I've put in the packet there. And then questions covering concepts and definitions from the entire quarter, okay? And the entire quarter. So so you know, students ask, is it cumulative? And the answer is kind of, okay? Definitely a heavy emphasis on chapters 7 and 8, which I believe form kind of the heart of statistical inference. And then there will be some questions covering concepts and definitions. So there's not going to be any calculation questions from chapters 1 through 6. So you're not going to have, you know, find the binomial probability, or, you know, what's the probability if this event is independent of this event. And, so there's not going to be any kind of calculation questions. It will be mostly conceptual questions. So things related to, yeah, I don't know, regression and describing distributions, some definitions thrown in there, stuff like that. Okay, and so I gave you know, a few examples of what those type of conceptual or definition-based questions might look like. Okay, so no calculations from chapters 1 through 6, but definitely concepts and definitions there. Okay, are there any questions I guess before we dive into conceptual stuff for chapter 7 and 8. Feeling all right? Okay. What are you guys' plans for after summer session ends and before fall quarter begins?
Have fun.
Having fun? Okay. I mean, that's good. I guess I was hoping for something more specific, like, I don't know, anyone planning to go back home, travel, anything like that? Just sit and watch TV, binge Netflix or something? I don't know. Okay. Oh, and then I will provide this table of formulas. This will be provided to you on the final exam. So as far as memorizing what the formulas for standard error are, I mean, you can, but you don't have to. This will be provided here, okay? And then the different z-star values, the z-score values for the hypothesis test for the different confidence levels are here. So most frequently we've been using 95% with 1.96, but again, the other levels, the z-stars, you can have 90%, 99, 80%, and those are all given here as well. Okay, and then I'll also provide the z table as well on the exam. So you just have to make sure you bring your calculator and something to write with. Okay, I'll provide the Scantron forms or whatever, and that should be it. Okay, all right. Well, let's get into this conceptual stuff. And so just kind of going back to a hypothesis test. Whoa, I did something. All right, let's forget this. Start a new paper. Okay. I know what's going on. It's my pen has this button that sometimes I accidentally touch. All right, okay, so anyway, okay. Okay, so in a hypothesis test, you can have hypothesis test with one sample, and if you do, your hypothesis is going to be P is equal to some number, so maybe like 0.42, okay, just some example number, and then the alternative will be something like P is not equal to 0.42, okay? I guess the in the general form would be P is equal to some number P0, okay? Again, the alternative can have a greater than or a less than or not equal to sign depending on the question. So it could be something like we believe the population proportion is 0.42, blah, 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 blah. We gather data, et cetera, et cetera, et cetera. And then we ask, does the data provide evidence evidence that the proportion, and then, so if you get words like is different from, or has changed, etc., these would be the not equal sign. On the other hand, if you have something is greater than, has increased, stuff along those lines, you would use larger, is less, has decreased, anything indicating something like that, we might choose a less than sign. Okay? And of course, you know, we have all sorts of other words in the English language to describe things getting bigger or smaller, and you just kind of have to read the statement carefully to see, is it, you know, are we using the greater than, less than, or not equal to sign. Okay. When we use the not equal sign means we have what we call a two-tailed test. Two-tailed or two-sided test. And then the greater than or less than sign means we have a one-tail or one-sided test. And the difference comes when we are calculating our p-value. Okay. And so when we talk about our p-values, maybe it's helpful for us to kind of review what exactly a p-value is. So we're talking hypothesis tests. And the p-value. So the p-value, this is the probability of observing our data or something more extreme if we assume the null hypothesis were true. Okay, so that's going to be the definition of our p-value. Okay? When the null hypothesis is true, it generally means that the random process is responsible, only the random process is responsible for variation that we see in our data. Okay. Only randomness is responsible for the variation. Okay, and so what this means is that we will look at our p-value, and this will give us an idea of whether or not we can believe that the null hypothesis is true. Okay, so a large p-value means there is a high probability of getting our data from randomness alone. Okay, so this tells us that we have no reason to doubt the null hypothesis. On the other hand, a small p-value means that there's a very low probability. There's a low probability of getting our data from randomness alone. Okay. And therefore, the fact that we actually have observed this data causes us to doubt the null hypothesis. Okay, because the null hypothesis says that randomness alone is what produced our data. Okay, and if when we do the calculations, we find out that it's really unlikely for randomness alone to produce the data. And so the fact that we have this data says, you know what? I don't think my data was produced by randomness alone. Okay? So small p-value means that there's a low probability of getting our data from randomness alone, and the fact that we've actually observed this data causes us to doubt the null hypothesis. We do not believe our data is a result of randomness only. Okay, so let me, I'll do kind of just a silly scenario here. We're trying to relate the idea of high p-values and low p-values, okay? So, let's say you decide to play a silly game, okay? Okay, you flip a coin, All right? Heads, you win. Tails, you lose. Okay? And I don't know, maybe you go to the county fair or something, they've got these booths, right? And there's the question, you know, are the games rigged, right? Are the games rigged? And maybe they're rigged, maybe they're not, right? So, okay, so we'll say, you know, you play at a booth, and then you just want to know, is the game rigged? Is the game rigged? So meaning, is it set up in such a way that the coin is not a fair coin, right? That the coin is not fair. And instead, you know, is it designed to give you we'll say give the booth owner an advantage. Okay. All right. So let's say you play 5 times. Okay. And out of the 5 times, you lose 3 times. Okay. Do you feel like this is evidence that the game is unfair? Okay, so technically you lost, you won only 40% of the time. Okay. Okay. So you play 5 times, you lose 3 times, so you only won 2 out of the 5. You only won 40% of the time. And you say, well, if it were a fair game, I should win 50% of the time, okay? So you're winning less often than what maybe the rules of probability say. So does this mean that the game is unfair? What's your feeling? Would you report this game booth to, I don't know, the county fair supervisor and say, these people are cheating? No, right? This doesn't seem like a unusual outcome. Seems like a perfectly reasonable outcome. And so here we ask, just from an objective standpoint, okay, what our null hypothesis in our case, what would our null hypothesis be? What would we say? We would say the null hypothesis is that the coin is fair. That the probability of winning is 0.5. P is the probability of winning. P is 1/2. Okay? That's the null hypothesis. The null hypothesis always has to be written with an equal sign, so we have to say that P is equal to something, all right? And then the alternative, what would our alternative be? Okay, we want to know, is the game rigged? Is it set up in a way that the coin is not fair, or is it designed to give the booth owner an advantage? So what would we say? That the probability of winning for the player is is less than 0.5, okay? So we're going to say the game is rigged against the player, or we would say that P is less than 0.5, right? If it turns out that the booth owner had made a mistake and they rigged it to be to give the player an advantage, this would not upset us, right? We would not complain to the county fair. I don't know if there's some kind of gaming commission for the county fair, but we would not go to them and complain, okay? We'd say, oh, everybody should play this game and take advantage of the fact that you've got a greater probability, right? We only get upset if we find out that they're doing something that disadvantages the player, okay? So here we would only be upset if it turns out that the coin is set up in such a way that it's gonna land heads less than half the time, okay? So these are our hypotheses, and when we do our calculations, our p-value, I don't know, turns out to be, okay, I'm just making this up, okay? I guess I could do the real calculations, but I don't feel like it, okay? But let's say, turns out to be 0.32, okay? I made this number up. Okay? The p-value turns out to be 0.32. Okay, so what does this mean? Okay, it tells us that if someone else were to come along and play a kind of the same setup and they used a real fair coin, okay? So we know that the coin is fair, it's not a rigged setup, okay? If someone else played the game 5 times with a real fair coin, they might lose 3 times or more than 3 times, okay? And that would happen about 32% of the time, okay? So let me just write this. Play 5, lose 3, okay? And we're gonna say p-value, all right, and this is, again, just made up, 0.32, okay? And this just means if a person played the game with a truly fair coin, okay? So basically, we're playing the game with the assumption that the null hypothesis is true, okay? So we're playing the game when the null hypothesis is actually true. If a person played the game with a truly fair coin, that person could still lose 3 games out of 5. Okay, or lose even more. Okay, could still lose 3 games out of 5 with a probability of 0.32. Okay, so the p-value again is the probability of observing our data or something more extreme if the null hypothesis were true. Let me find that slide. Again, here's the definition of the p-value. Put that right there, okay? Okay, so it's saying the probability of observing our data, that is losing 3 games out of 5 or something more extreme, if the null hypothesis were true. So if the null hypothesis were true, that means someone's playing with a fair coin, and this could happen with a probability of 0.32. So that's a non-negligible probability, okay? That means it happens about 1 in 3 times. And so at this point, we're going to say there's not a trivial probability, okay? We cannot ignore the possibility that our results, losing 3 out of 5, was just a result of randomness, okay? Our, unfortunate outcome, our outcome of 3 losses out of 5 was just a result of randomness and bad luck. Okay. Now, does this prove that the game is actually fair? So right now we say we don't have evidence that the game is rigged, okay? Playing 5 games and losing 3 does not provide evidence that the game has been rigged against us. Okay? At the same time, does it prove that the game operators are running a fair operation? Okay, so our p-value is 0.32. So we say p-value equals 0.32. And we'll say we do not reject the null hypothesis. But someone asks, so here, let me just kind of write this. So we can say, do we have evidence that the game is unfair? And the answer is no. Is that okay? Because our results of losing 3 out of 5, that could be a result of just randomness. On the other hand, do we have evidence that the game is fair? And the answer there is also no, okay? It's just playing 5 games and losing 3. That doesn't provide much evidence either way, okay? It doesn't prove that the game is unfair, but it also doesn't prove that the game is fair, all right? And there's actually no way to really find out if the game is fair unless you like do a full inspection and check everything out. And that's tough. So based on data alone, we can never actually prove that the null hypothesis is true, okay? So let me just write that. We are never able to prove that the null hypothesis is true. All right, so that's one silly example. Let's just take this to the extreme, okay? And let's say instead of 5 games, you decide to play 5,000 games, okay? Or maybe not even. We'll do 500 games, okay? You play 500 games at the same booth. Okay, and we'll say again, you win only 40% of the games. Okay, that is to say you win 200 and lose 300. Okay, and the question is now, do we have evidence that the game is rigged against the player? Okay. So what's your gut feeling now? So you played, before we played 5 games and we lost 3, we won 2. We won 2, we lost 3. And we said, maybe we had bad luck. Okay. Now we've played 500 games. We're just flipping coins. We want to see how often we get heads and stuff. And this time we won 200 games and we lost 300 games. Do you think we just had bad luck again? Okay. Well, I would say that it seems a lot stranger to get these results. Like, this doesn't sound like bad luck anymore. This sounds like the game, someone's cheating here, okay? And for causing us to lose a little bit more often, right? So do we have evidence that the game is rigged against the player? So again, we set up our hypotheses the same way. The hypotheses are, the null hypothesis is that P is 0.5, you know, the coin is fair. And the alternative is that P is less than 0.5, right? Coin is rigged against the player. Okay, and so so here we would just say, so we might do our calculations, okay? Calculations, et cetera, et cetera, et cetera. And our p-value, again, I'm making this up, but let's say is 0.0001, okay? So again, I made this number up. Okay, don't actually try to calculate this, all right? And so what this says is that if the null hypothesis were true, okay, meaning if someone plays with a fair coin, so if the null hypothesis were true, or if someone's playing with a fair coin, could they get the result where they win only 200 games out of 500? Okay. It is technically possible to get only 200 wins out of 500. Okay. But it happens with a probability of 0.0001. With a very low probability of 0.0001. All right. And so the fact that this probability is so small, and the fact that this actually happened, gives me reason to doubt that this game was played with a fair coin. Okay? So I could say, well, that's what happened to me. I only won 200 games out of 500. Maybe I was the lucky 1 in 10,000. Okay? But more likely, it's not that I was the lucky 1 in 10,000 or the unlucky 1 in 10,000. But more likely the case is there's something a little strange going on about this game. And that's the reason for my incredibly low number of wins. Okay? So, you know, so I could say I could be, okay, I'll say, you know, this is what happened, okay? This is what happened in my data. Okay, I could be the unlucky one in 10,000 to have the low win rate. Okay, but a more likely explanation is that the game is rigged, and that is why I have such a low win rate. Okay. Does this logic make sense to you guys? Right? So when the probability of our data is low, that's when we say, I have evidence that something is happening, that it's not a result of randomness. Okay? Because we're just saying, could it happen from randomness? It could, but it's really unlikely. Okay? So I could just go away and say, well, maybe I was that unlucky 1 in 10,000. Okay? Okay, but a more likely explanation is that I'm not the unlucky 1 in 10,000, but rather that the game is rigged. And that is what explains my incredibly low win rate. Okay? So the conclusions are, when the p-value is large, we do not have evidence to reject the null hypothesis. Okay. And when the p-value is small, okay, so again, p-value is the probability of our data if the null hypothesis were true. So if the probability of our data is large, we don't have reason to doubt the null hypothesis. Okay? And on the other hand, if the p-value is small, we say we have evidence to reject the null hypothesis. And so this is where significance level comes in. Okay, we talked about the significance level alpha. Alpha is kind of this arbitrary line that we draw, and this is going to be the threshold between what p-values are large and what p-values are small. Okay? Okay, so most frequently, alpha is equal to 0.05, okay, 5%. But this is just an arbitrary number, and I think it's that because we've got 5 fingers there, right? A lot of a lot of our number system and math and the rules we pick are based on the fact that we've got 10 fingers, right? And here I think, you know, we've picked alpha as 5%, and that's just an arbitrary number. Probably should be something around there, but it's not necessarily the best number for all cases. But alpha is most frequently 5%. And when the p-value, when p-value is large, meaning that the p-value is greater than alpha, we do not reject. And when the p-value is small, meaning the p-value is less than alpha, we have evidence that the evidence to reject the null hypothesis. Okay. Most frequently, alpha is 5%. However, we may choose to use alpha equal to 0.01, or sometimes even alpha greater, alpha at 0.10, or some other arbitrary value. Okay. So alpha is just an arbitrary value, all right? We have arbitrary values that form boundaries all the time, okay? But alpha 5%, so often if the p-value is bigger than 5, we say do not reject the null, and if the p-value is less than 5%, we'll say reject the null hypothesis, and that's kind of how it goes. But somebody else can say, you know what, alpha should be this number, alpha should be that number, right? It's kind of, you know, we have arbitrary numbers, and we just kind of accept it in life, all right? The p-values and alpha isn't the only thing. Drinking age in the United States, arbitrarily selected to be 21 years of age, okay? And we just go with it, right? But if you go to a different country, that number might be different, okay? You go to Canada, drinking age I think it's 19. I don't know. Other countries it's different. And probably the number should be something around 19, 20, 21, I don't know, okay? Some number around there. I think Japan is 20, okay? So, you know, it's based kind of on science-ish stuff, right? They say, you know, your prefrontal cortex continues developing and whatever, something around age between 20 and 25 or whatever is when it's fully developed, and I guess they want to keep alcohol out of, I don't know, all right? In the US, we've arbitrarily picked 21 as the number, and we've kind of accepted it, all right? And in statistical research and stuff, 5% seems to be the number that most people go with, and it works. But you get weird, but anytime you draw a weird, an arbitrary line, weird things happen, okay? So another example is retirement age. Well, in the US, you get your full Social Security benefits at age 65, okay? And so this has kind of unofficially become the line for retirement. And so, are there people who are fully capable of working and being productive past the age of 65? I'm sure there are, okay? However, because full Social Security benefits kick in at 65, there's no incentive for anybody to work past 65. And so if somebody is, I won't say no incentive, but if, you know, if someone is in a position to retire, then a lot of people will, you don't find very many people working after age 65 if they're able to financially support themselves, because there's the maximum benefits have filled in. And so there's kind of this arbitrary line at 65, a whole bunch of people retire, very few people work past that, and there's almost kind of an expected mentality of, oh, you're working and you're 68 years old? That seems strange. So, you know, yeah, whenever you draw an arbitrary line, things happen. But 5% seems, probably should be something around 5%, but you also get these weird side effects of that, in that if you look at scholarly research that's published, a lot of times the threshold to get your thing published is that your p-value has to come in less than 5%, okay? And if it's less than 5%, the journal is willing to publish your research. If it's bigger than 5%, they're not. And so you get a lot of research articles published with p-values of 4.9%, 4.8%, 4.7%, that they just barely made the threshold, and so they can get their thing published. And this has led to another problem of reproducibility, and maybe things that were just random results and had a 4.8% chance of being a random result is getting published now. But let's talk a little bit more about this significance level alpha, okay? So the researcher gets to choose alpha. Okay? And so why would a researcher want to pick a large alpha or small alpha? Okay? So okay, should the researcher pick a large or small alpha? Okay? Well, alpha is also equal, alpha, which is the significance level, is also equal to the risk, or the probability, of making what we call a type 1 error, or also known as the false positive. Okay, it turned out, when hypothesis tests were being developed, this was 1900s, like 1920s and stuff like that, or early 1900s. Fisher and these other people working on it realized that there are two types of mistakes that they can make, two types of errors. And they did not have creative names, so they called them the type 1 error and the type 2 error. Okay, later on we came up with better names like the false positive and the false negative, but unfortunately, kind of the generic names of type 1 and type 2 error have stuck around in the literature, and so we still have to call them that, okay? But type 1 error is unfortunately not descriptive at all, and it doesn't really tell you. False positive, at least, that gives you a sense of what that is. Okay, so what is a type 1 error? So the type 1 error, or the false positive, okay, this means that in truth, okay, because we're always seeking the truth, okay, or we should be, in truth, the null hypothesis is true. Okay, so in reality, or in truth, the null hypothesis is true, but our data has led us to the conclusion to reject the null hypothesis, okay? But our data, okay, probably because of random chance, okay? Led us to reject the null hypothesis. Okay? So the null hypothesis is actually true, but when you went out and collected data, because of randomness, something happened and it led you to believe that the null hypothesis is wrong. Okay? That can happen because, again, our data is a result of a random process, you know? So the truth is maybe, I don't know, you're comparing the brand name product to the store brand, right? You go to Costco and they've got like the brand name and they've got Kirkland's signature or whatever, or you go to Walmart and they've got the brand name stuff and what is it, Great Value at Walmart or something, okay? And so you want to know, like, are these the same or are they actually different, right? And let's say you go out and you do some kind of test, and maybe the truth is that the brand name and the generic thing are actually exactly the same. Sometimes some factories will produce all the stuff and they just put different labels on them and they sell them at different prices, okay? So maybe the truth is that it's coming from the exact same factory and it's just they changed the labels up, okay? Maybe that's the case, right? But when you did your random sampling, okay, and you did your random thing, maybe because of just something weird that happened in your random sampling process, you come to the conclusion that there's a difference, all right? That's the wrong conclusion. The truth is that the same factory is producing everything, but you came to the conclusion that there's a difference, all right? So that is what we call a type 1 error. And whatever alpha level you choose is going to be the risk of type 1 error, okay? So if you've picked alpha to be 5%, you have a 5% chance of making a type 1 error. If you increase alpha to 10%, you're going to make type 1 error with a risk of 10%, okay? And if you decrease alpha down to 1%, you'll make type 1 error only 1% of the time, okay? So the question is, well, why don't I just pick a really small alpha? Or why don't I just set it to 0? I don't want to make this kind of mistake. If it's coming from the same factory, I want to, you know, I don't want to come to the wrong conclusion, okay? Well, what's the problem with that, okay? So why don't we avoid type 1 error by simply picking a small alpha? Okay, because you could do that. That will work. If you want to reduce type 1 error, just pick a small alpha, okay? But why do we pick alpha as 5%? Why don't we just pick alpha to be something really tiny, okay? Well, when we reduce type 1 error, the risk of type 1 error, we increase the risk of the other kind of error, the type 2 error, the false negative, okay? So when we reduce alpha, okay, we increase the risk of a type 2 error, a false negative. Okay, and so we have beta. Beta is the probability of making a type 2 error. Okay, so alpha is the first letter of the Greek alphabet. Alpha looks kind of like the letter A. It's the first letter, that's the type 1. Beta is the second letter of the Greek alphabet, looks like the letter B. Okay, so that's how you can remember A, alpha. A is the first letter and it looks like alpha. B is the second letter and it looks like beta. That's actually where we get the name alphabet, is from alpha and beta, just stuck together. So anyway, alpha is the probability of type 1 error and beta is the probability of a type 2 error. So what is a type 2 error? the type 2 error which is our false negative, this is kind of the other kind of mistake, okay? So in reality, the null hypothesis is false, okay, and should be rejected. Okay. However, our data, okay, either because of random chance or we just don't have enough data, however, our data does not lead us to reject the null. Okay? So our data just says, all right, well, I'm not ready to reject the null. Okay? So if we think back to this carnival game with the coin flips, okay? And the first time we ran the test, okay, we played the game 5 times and we lost 3 times. Right? And so when we did that, we came to the conclusion that we do not have enough evidence to say that this game is, that the game owner is cheating, okay? Playing 5 games, losing 3, we said, all right, we don't have any evidence that they're cheating, okay? Or we don't have enough evidence that they're cheating. However, if it turns out that they were cheating, then we made a type 2 error, okay? Ideally, we wish we would have caught them cheating, but maybe playing 5 games wasn't enough, okay? Maybe we had to go out and collect more data. We had to play 500 games or something to come to that conclusion. But so if we go out, we do an experiment, and we come to the conclusion that we should not reject the null, we're not ready to reject the null, and that turns out to be wrong, that's a type 2 error, okay? Let me, here's like a little joke. Let me see. Let's see, type 1 error, pregnant. Let's see if we have the, all right, here's our meme of the day. Can you guys see this? Okay. All right. One person left. Thank you. Okay, so here the null hypothesis is the patient is not pregnant. Okay, and then the alternative is that the patient is pregnant. Excuse me. And so the type 1 error is the false positive. We reject the null, but in reality the null is true. Okay, and over here the type 2, okay, we did not reject the null, but in reality the null is false. Okay, and technically it shouldn't be, to make this correct, it should say we do not have evidence that you're pregnant rather than you're not pregnant, because we don't ever say the null hypothesis is true. Okay, it should really, to make the joke correct. I'm like the worst person, right? Like, actually, it's not like that. So the doctor should say, we do not have evidence that you are pregnant, okay? Yeah, you know. I am a pedant after all. All right, okay. So we'll say we do not have evidence that you are pregnant, okay? Of course, I have to be the one that corrects jokes to make them technically accurate. But all right. But anyway, this is how it goes. All right. So that would be the type 2 error, okay? If we say, you know, we do not have evidence to reject the null, but in reality, okay, obviously this woman is pregnant, or at least putting a basketball under her shirt. We say you are pregnant, okay? So that's what we have there. All right. And so I think we started off on this going back to the question of when do we want to pick a big alpha or a small alpha, okay? And the answer comes with, so we find that alpha is related to the risk of type 1 error or the risk of a type 2 error and things like that. So anyway, so we say alpha is equal to the probability of type 1 error, and beta is the probability of a type 2 error. Okay, and so when do we want a, so should we pick a large alpha or a small alpha? Okay, and the answer depends on, is it better or worse to make a type 1 error or a type 2 error? Okay, so depends on the consequences of a type 1 or type 2 error. Okay, so if type 1 error is worse than type 2 error, okay, so if the type 1 error is worse than the type 2 error, would we rather have a higher, we would rather have a low risk of type 1 error, right? We would rather have low risk of type 1 and higher risk of type 2. So we would pick what? Big or small alpha? Small alpha. Okay, and if type 2 error is worse than type 1, we would pick what? Big alpha, right? Write this to make it look a little bit better. Okay, so if the type 1 error is worse than the type 2, we'll pick a small alpha. If the type 2 error is worse than the type 1, we'll pick a big alpha. Okay, so what's so let me give you an example. All right, so think of our justice system, okay? So the null hypothesis, all right, so we'll say, so imagine a criminal trial in the US, okay? All right. So, I don't know if you guys ever, there used to be a TV show called Cops. And they would follow around like these police officers that would go around arresting people. I don't know if anybody ever watched it, but it had a catchy theme song. It was Bad Boys, and that's where we got the Will Smith movie, which they're making a third installment of the franchise. Okay, anyway, it doesn't matter. Will Smith and Martin Lawrence, right? And Bad Boys, and so it comes from, yeah, anyway, all right. Anyway, at the end of the show, they always said, whenever someone was arrested, they would say the defendant is always presumed what? Presumed innocent until proven guilty in a court of law, right? And so, in a criminal trial, what would our null hypothesis be? That the defendant is innocent or guilty? Okay, we're going to write the defendant is innocent. Okay, and then the alternative is that the defendant is guilty. Okay. All right, so ideally, the ideal scenario is all guilty people are convicted. Okay, so that means we reject the null when the null is false. Okay, and all innocent people are acquitted. Okay, that means do not reject the null when the null is true. Okay, that's what we want, right? We want guilty people convicted, innocent people let go, innocent people acquitted. Ideal scenario. Okay, but we don't live in a perfect world, okay? So there's crimes in the first place, and sometimes the justice system makes mistakes, okay? All right, so what is a type 1 error? Type 1, the false positive. Yeah, the type 1 error is we've rejected the null, okay, meaning that we have come to the conclusion that the defendant is guilty, but in reality, the null hypothesis were true, okay, that in reality, the defendant is actually innocent, okay? So type 1 is convicting an innocent person. Okay? What is a type 2 error? Okay, yeah, type 2 is letting a guilty person go free. All right, so this is always up for debate. But at least the way our justice system is set up, which of these errors is worse than the other? All right. Well, okay. Let's just take it to the extreme. All right. So let's say this is like a death penalty case, right? So if you say guilty, the person's going to be executed, and if not, the person will not be executed, right? Will be let go. All right, so which error is worse here? Type 1 error is worse, okay? And that's there were some documents in the founding of our country and things like that basically reflect this viewpoint, that the type 1 error is worse than the type 2 error. and you know, that's what the whole due process is all about. Okay, so that, you know, someone will not be held without due process and things like that. That's what we've said. Okay, type 1 error is worse. And so in this case, do we want a small alpha or a big alpha? We want a small alpha. Okay. And they actually say this in trials, I think, at least what I've seen on TV, right? They don't tell the jury, use a small alpha in your decision making, okay? But they do say something along those lines. What do they say? Nobody watches, yeah, I don't really watch crime procedurals, but what do they say? Here's a phrase talking about beyond a reasonable doubt. Okay, so when they say, so what do they mean by beyond a reasonable doubt? Okay, this means don't convict somebody because you've got a hunch, right? Because you just feel like the person's guilty. They don't want people convicting people based on that. They want that the evidence is so much so that it cannot just be explained by circumstance. That the only explanation that's reasonable is that the person is guilty. Okay, that's the only reasonable explanation for the evidence provided. And if there's a case where the prosecution doesn't have any evidence, okay, then the judge will just dismiss the trial, right, and say, we've got to let the person go, right? Now, if a person is acquitted, does that mean that the person is innocent? No. A not guilty verdict does not mean that the defendant is innocent, okay? The jury will never say, we, the jury, find the defendant innocent. They just say not guilty. And that just means there wasn't enough evidence to bring about a conviction, okay? There might be evidence, but maybe this evidence can be explained by random chance, okay? Maybe some strange circumstance that seems plausible can explain the evidence. And that's what the defense attorneys are supposed to do. They're supposed to be able to take the evidence that the prosecution presents and explain it away and say, this is the reason why, okay? Is it strange that, you know, the defendant's DNA showed up at the crime scene? Yeah, that's strange, but maybe here's a reasonable explanation. Maybe the defendant happened to be cleaning at the place, or maybe the defendant had some different relationship or something, and that's the explanation for why the DNA is there, right? But then maybe as the evidence amasses, then it gets more and more strange to try to explain away, and maybe the defense can't do that, and that would bring about a conviction, okay? Not rejecting the null does not mean the null is true. Okay, just like not guilty does not equal innocent. Okay, so in that case, we would want to pick a small alpha, and it's reflected that way. All right, is that all right? Let's go ahead and take a look at some of these practice questions. Oops. Can you guys see this? All right, let's go with the let's go with the first question here. All right, why don't you here, let's just do these first two questions, okay? Okay. Pick A, B, C, or D, and then number 2, pick A, B, C, or D. Okay, so the significance level alpha is used to decide whether or not to reject the null hypothesis. What else is alpha equal to? So alpha equals the probability of a type 1 error, which is our false positive. And so what is the result there? It is C. Mistakenly, we've rejected the null hypothesis when the null hypothesis is true. Okay. All right, and beta is the probability of a type 2 error. This is the false negative. So again, think back. Maybe if you think of the pregnancy thing. Okay, and what's our answer there? Yeah, also C, okay? The probability of mistakenly not rejecting the null hypothesis, okay? So we say we did not find evidence that you are pregnant when the null hypothesis is false, okay? When the person actually is pregnant or something like that, okay? So that could be a case where, I don't know, somebody takes a pregnancy test like too early, right? So sometimes if you take a pregnancy test too early, it might come back and say no evidence that you are pregnant, okay? But the person actually might be pregnant, right? So it's usually, I think the earliest is like 26 days after, I don't know, last, whatever, okay. All right, what is, oh, this is the example we did. Okay. Should have done a different example. What's a type 1 error? So this is like the same question as question 1, but phrased differently. Okay. So type 1 error, again, is a false positive. Okay, and so that means we've rejected the null hypothesis, but the null hypothesis is true. Okay, so we've got there. Let's take a look here. So we've got criminal court case. Set up defendant is innocent, defendant is guilty. type 1 error is worse or type 2 error is worse? And do we want a big alpha or small alpha? Okay, so the type 1 error, again, is the false positive, which in this case is convicting an innocent person. Convicting an innocent person, which is convicting is reject the null hypothesis when innocent person when the null hypothesis is true. Okay, and that's worse than the other. Type 2 is let a guilty person go free. So we do that, right? The counter argument is, you know, if you let a guilty person go free, they might go out and commit another crime, and there will be another victim. Let me, an aside, so let's say there's a judge, goes, you know, judges things and maybe convicts someone, and that person goes to prison, serves, you know, 20 years in prison or something, and then it turns out that the person was innocent. Right? Sometimes we find out these stories make the news, right? So-and-so, this person is let go after, you know, serving something for, you know, an innocent person is let go after serving time for a crime they didn't commit, okay? And so let's say that gets back to the judge who made that decision, because some trials are decided by a single judge, and maybe that judge says, I never want to make that mistake again, okay? It's a reasonable feeling, right? The judge feels guilty about convicting an innocent person, says, I never want to make that mistake again. What is the only way the judge can avoid making that mistake again? Of convicting an innocent person. Yeah, the only way the judge can completely avoid ever convicting an innocent person again is by never convicting another person ever. Okay, that's the only way a judge can fully avoid making the mistake of convicting an innocent person, right? The judge can say, all right, I'm basically going to reduce my alpha to 0, so I will never make a type 1 error, okay? And the only way you can fully avoid type 1 error, right? So if we pick alpha equal to 0 to avoid type 1 error, what that means is that we will never reject the null hypothesis. Okay, because the only way to reject the null hypothesis is if the p-value ends up less than alpha, right? And so this is akin to a judge who never wants to convict an innocent person. Okay? And the only way to avoid this mistake, to guarantee never making this mistake, is to never convict anyone. Okay? And if the judge never convicts anyone, if the judge always says not guilty, then that person is no longer a judge, right? That person's no longer making any decisions. It's just a rubber stamp that says not guilty, okay? A judge who always says not guilty is not a judge. Okay. That's the burden of being a judge. And the burden of being a jury is that someone's life hangs in your balance, or it's whatever. Depends upon you and your decision, and that person, you have to make the right decision, okay? So it's simply not possible. Type 1 and type 2 errors are just inherent to any place where we have to make decisions based on incomplete data, okay? And that's just all of life. It is not possible to avoid type 1 and type 2 error. It is inherent to life where we have to make decisions without knowing everything, right? And that's, you know, in life, you're gonna have to decide something, right? Should I enter a relationship with this person, right? That's a decision you have to make. And you can choose to enter the relationship, and it could turn out to be great. It could turn out to be terrible, right? You might waste 3 years of your life, and you're like, oh, why did I ever date this person? That was terrible for my life, okay? Or you could say, well, no, I'm not gonna enter this relationship. And that might be the right decision. Or it could also be a terrible decision, because maybe being in a relationship with that person would have been good for you, or not, who knows, okay? It's incomplete. You don't know what's gonna happen in the future, all right? So that's all of life. You don't know whether the person you're with now or the person you like now is gonna change or is gonna remain the same, okay? Everything is unknown. You have to make a decision, and it may or may not turn out to be the right one. And you just have to, everyone lives with different levels of alpha, right? Their acceptability, level of acceptable risk versus not, right? So choosing not to do something could be just as risky as choosing to do something. So anyway, this is what we've got. Type 1 and type 2 error are just inherent and unavoidable. I'll say that. Type 1 and type 2 error is inherent to the process of making a conclusion without all the data. Okay, so that's basically always. I guess the only way to avoid it is if you somehow gain knowledge of everything. Probably not possible in our reality. Okay. And I guess what Dr. Strange can do it. All right, here we go. Imagine a doctor diagnosing a patient. The patient undergoes some tests to detect cancer, and the test uses the following hypotheses, right? So in general, when you walk into the doctor's office, the doctor assumes you are healthy unless you show symptoms otherwise, okay? And so the null hypothesis is that the patient has no cancer. The patient is healthy, and if symptoms or tests come back, maybe the conclusion is that the patient has cancer, okay? So these are your null and alternative hypotheses. Okay, what would a type 2 error be in this scenario? So we have, so type 1 is the false positive. And type 2 is the false negative. Now, what would the false negative be? Okay, all right, so A, B, C, or D? What do you think? B. B is the answer, okay? We believe that the patient has no cancer, okay? So B is we did not reject the null, okay? Even though the null is false. Okay, that's what the false negative is. Okay. We should have rejected it. Okay, so that's a type 2 error. What's a type 1 error? What's a type 1 error? Type 1 is answer choice A, okay? We believe the patient has cancer even though he or she is actually in good health, okay? All right. What do you think, which error is worse, type 1 or type 2 error? Okay, I think we would say type 2 error is worse, okay? And if it's not cancer, if it's like some transmittable disease, okay, then the type 2 is like even worse, right? Because now you can get other people sick. But you know, type 2 is still worse here because you know, the patient needs treatment. The patient probably needs medical care, something, and a type 2 error means the patient does not receive the medical care attention that they need. Type 1 would be maybe the patient gets scared into believing they have cancer when in actuality that they are healthy. And I guess maybe the consequences, depending on like at what stage, right? If you're going to start some kind of drastic treatment like chemotherapy that has severe consequences on the body, you know, maybe starting that when somebody doesn't actually have cancer, that would be a terrible thing to do as well. But anyway, type 1 error is that, and we generally say type 2 error is worse than type 1, okay? And so that means we would pick what? Large or small alpha? We choose a large alpha, okay? Which basically means it only takes a little bit of evidence to reject the null, okay? It doesn't take a drastic amount of evidence. We choose a large alpha means we only require a little evidence to reject the null. Okay. Are you guys familiar with WebMD, the website? Okay. There's like jokes and memes about WebMD, right? Maybe. And I think the joke is that if you go on WebMD and you search your symptoms, it's always going to come back and say what? You're dying. You have cancer or something, right? And it's WebMD is just operating with a very large alpha, okay? Because WebMD knows it's not able to prescribe drugs to you, okay? So no one's going to be able to start any kind of drastic treatment for themselves, all right? And so they say their scenario is, which is worse? Tell somebody that they're healthy when they're sick, or tell somebody that they should visit the doctor when they're healthy. And WebMD says it is worse to tell someone who's sick that they're healthy than it is to send a healthy person to the doctor, okay? And so, so WebMD operates with a very large alpha and basically says, all right, any symptoms, you better go see a doctor, okay? You might be dying, all right? You better go see a doctor. And I'd rather make that kind of mistake than the opposite, where somebody who actually needs medical attention doesn't get it, okay? Because they know that you can't go to the pharmacy and say, well, please prescribe, I don't know, these narcotic drugs because WebMD says I'm sick, right? So at a first level, WebMD will operate with a very high alpha. Then you go to the doctor and kind of the initial screening, maybe you see a nurse practitioner or something, and then they say, okay, well, they operate with a lower alpha, and the levels of alpha keep dropping as the treatments get more and more drastic and severe, right? The doctor will have you go through a whole bunch of tests, gather a whole lot of evidence, okay, before starting a drastic treatment like chemotherapy for cancer, because they don't want to start that for anyone who's healthy. But you go through a barrage of tests before making that kind of thing, and each test basically operates at a lower alpha level. Okay. So when using a two-sided alternative, this means that the p-value will always be double. Well, okay, so here, let's... So again, the p-value is the probability of our data, or something more extreme, if the null hypothesis were true. Okay, and so let's say you do the work and you get, like, you know, p hat minus p0 divided by the standard error is equal to negative 1.82 or something like that, okay? All right, so this is our picture, negative 1.82. Okay, so if the alternative has we'll do has a less than sign, we take the area to the left of Z, which in this case, negative 1.82, and we shade that area. If the alternative has a greater than sign, we take the area to the right of Z, which in this picture is going to be weird. Okay, because we're on the negative side, negative 1.82, and the area to the right ends up over here. And if the alternative has a not equal sign, then you're going to go to the left of Z and to the right of the opposite sign. So you're going to take this and take this, okay? So the answer ends up being C. It might be greater or it might be smaller than the p-value of a one-sided alternative, depending on the alternative, okay? So, so this area is going to be double this, but probably less than this, okay? So, so this picture is double this one, but might be less than this one, okay? Might not be double that, okay? All right, let's knock out these last two. Okay. And then again, I will post solutions to the practice problems from chapters 7 and 8 that are available on week 5. Also attend section today and visit your tape. Okay, so hang on. Let's take a look at number 7. It says you perform a hypothesis test comparing proportions from two samples. The alternative states that the proportion of population 1 is different from the proportion of population 2. So our alternative is going to be P1 is not equal to P2. And you find that your p-value is greater than alpha. Okay? So if the p-value is greater than alpha, that means we do not reject the null hypothesis, right? So the only thing that lines up with that is we say that we do not have evidence that the population proportions are different, okay? Okay, do not reject the null does not mean that they are equal, okay? So don't conclude B, all right? And then C and D just don't line up. Okay, and then with number 8, it says you perform a hypothesis test with population proportions with that they're different. Alpha is 0.05. The test reveals that you would reject the null hypothesis, okay? So here, we have alpha equal to 0.05, and we rejected the null hypothesis. So that means our p-value, whatever it is less than alpha. It's less than 0.05, okay? We do not know the exact value, but we know it's less, that it's 0.05. Okay, all right. If we did the same test with the same data and had used alpha equal to 10% instead, what would we conclude? Okay, so same test, same data means we will get the same p-value. Okay, and so this p-value, which we don't know, is the p-value less than 0.10. Okay, we don't know the exact value of this thing, but we do know it's less than 5%. And so is it less than 10%? Yes, it has to also be less than 10%. So we would reject H0, okay? Okay, so we do know it's less than 5%, so the p-value is less than 0.05, so p-value is less than 10%, which leads to reject null. Okay, we'll end there. We'll see you guys on Wednesday. Good luck as you guys study, and we'll see you then.